is Alan Verdegraal. I've submitted a paper on determining the primality of N-1 and M+1 solely based upon examining the structure of the natural number N. If there are any questions, feel free to email me. I have my email address up there. It's a and my last name at gmail.com. Primality is defined simply as determining if a number is either a prime or a composite. The methods presented in this paper show how primality can be determined without using factorization or sieving, which are the classical ways of determining if a number is prime, or even using multiplication or division. Primality can be determined simply by using modular addition. This research took place during 2022 and 2023. This paper presents the very last finding of this research. Since this is a multidisciplinary conference, I invite everybody's thoughts on how this research can be applied to particular industries. So the theory starts off very simply, the natural number line. One of the first math concepts we all learn in school at the earliest age. Numbers follow each other one by one on the number line. And the paper, though, proposes that we look at numbers not just as points on the number line, but as distinct entities within themselves. We can do this by visualizing a circle surrounded by any number of points. Let's number them from 1 to n. This circle is a representation of a natural number. So you see down here, and let me get the pen going. You see down here that number 5 is represented by 5 points, and they're numbered from 1, 2, 3, 4, 5. So this is a representation of the natural number 5. So let's play a child's game of counting around one of these circles. I'm trying to get to the next slide. For some reason, I'm having difficulties. Pardon me. There's the last one. Okay, here we go. So we have the number 5 represented as a circle with 5 numbered points. And we're going to count around the circle using increments. And if we use an increment of 1, we get the numbers 2, 3, 4, 5, 1. Let me get my laser pointer again. And then if we count by 2, we get the numbers 3, 5, 2, 4, 1. And if we count by 3, it's 4, 2, 5, 3, 1. And by 4, it's 5, 4, 3, 2, 1. And the last row is always going to be just all ones. And notice that over here, there's this separate column. It's called the orbit value. And that's the number of times we actually have to go around the circle before we end up back at the starting point. So it varies depending on really how many times we go around. If we look at this 4th row here, we start off at 5, we're counting 4 to 4, and then again to 3, again to 2, and finally to 1. That's 4 times around the circle we had to go. Now, I'm actually not going to talk about the orbit values of these rows. That did end up being 95% of the research that took place during that 2-year period. And we're going to focus just on this square array of numbers. And the first thing we're going to do is get rid of these ones. You know, they're sort of redundant, meaningless in a sense, but I guarantee you that 1 will become very significant in this theory within just a few more slides. Let's focus on this smaller array, which is in white. And this one happens to be what is called a Latin square. Latin squares were originally identified by Leonhard Euler in the 1700s. And a Latin square is where each number or symbol appears only once in each row column. If you look, you can see that each member of this particular array meets this criteria. If you look at 5, for instance, it is unique for its row column. All the 5s are only there once for each row column. These arrays can get quite big very fast. Since it is an exponential, we don't have to deal with these numbers though, because the computer is going to deal with them. We can have computer programs that will search for patterns in these square arrays. So I'll go over very briefly how you can program a computer to generate these arrays. First, we define what is called an additive increment array, and that's the numbers from 1 to n-1. For if we're looking at, say, a number such as 13, so it'd be 1 to 12. And then the first row is always defined to be 2 to 13, or 2 to n. And then what we do to get the second row is to add these 2 arrays together. And then we can use that additive increment array again to add to the second row to get the third row. And then keep on going all the way down until we complete the array in itself. And so we get this array of numbers. And as I've mentioned before, if n is a prime number, this square, and we're calling it square SQ of n, is a Latin square, and vice versa. If we can show that this array is a Latin square, then n must be prime. Now, what about composite numbers? Let's look at a few. If n is a composite number, then there is a specific pattern of 1s that appear in the array. The left array, for instance, is for n equals 14 and has a distinguishing cross of 1s that appear. And the right one is for n equals 15, and it actually has 1s that appear in all 4 quadrants. These squares for both prime and composite numbers have some interesting symmetry properties that will apply quite soon. The squares are always symmetric along the diagonals. So if we draw a diagonal here, we can fold the array and the numbers match up. For instance, see this 11 here? It will match up with the 11 up here. And the same thing with the 2 10s, they match up. All the numbers mirror each other along the diagonal. And the same thing with the other diagonal. See, this 2 is going to mirror the 2 over here. And the 3 3s, or the 2 3s, I mean, they will match up. So we can fold the array along the diagonals and the numbers will match up. But this doesn't apply to the XY axis. If we fold the array on the X axis, the numbers don't add up. 11 does not match with 2. And if we fold it on the horizontal axis, they don't match up either. This 11 does not match up with 2. However, the ones that appear in composite numbers do match up if we fold it. The ones form an invariant group regarding this composite square. We can fold it, we can turn it, we can flip it, we can do all sorts of things, rotate it around, and the ones will always appear in the same spot in these arrays. And the pattern of ones will never change. And this gives us some interesting ways of testing for primality. We've already sort of discussed one, which is the Latin square test, where we actually would go through the array and test every single cell to see if it's a unique symbol or number for that row column. And if we actually were to do that and get to the very bottom, and indeed all the numbers are unique in their row column, we have demonstrated that this is a Latin square and that the number n would be prime. Now, we don't have to search the entire array, though. Because of the symmetry properties, we actually can search only half of it based upon either the diagonals. And because we can actually merge those two together, we can search only on like a fourth of the cells within the array. And because of the ones are symmetric around the XY axis, we can only really need to search 1/8 of the array. And what are we searching for? We're searching for a value of 1. Because if we find a cell with a value of 1, we know we have a composite number. It's not a prime number because prime numbers will not have any ones within the array. Symmetry only allows us to check the small sector looking for a 1. So in the research that I did, I came up with an algorithm. It's called the temple search algorithm because it sort of looks like a man temple. But we don't have to search and test every one of the cells because these cells that are in yellow, by definition of the construction rule, will never have any ones. Only the white section will have a possibility of having a 1. And I was able to devise an algebraic expression that basically has 2 indexes, one for the row column, and so we basically just literally march up the temple, testing each one to see if it is a 1. And if it is, then it's a composite. We can get out of our algorithm and we know we have a composite number. If we reach the top and we do not find a 1, this is a prime number. And so that sort of completes our search. But still, if we're dealing with large numbers, this will still be a large number of cells to test. So we observed something very interesting that I have called the staircase conjecture. See this green band here? It's formed by part of the main diagonal and the diagonal underneath that main diagonal. I observed that for a composite number, there is at least one in this green zone. And so we only have to test this green zone for a 1. Now, this is a conjecture because it hasn't been proved. And I hope that a mathematician will get curious enough one day to actually demonstrate either the proof or disprove this conjecture. But it has been tested for all primes up through 10,000, and then the count of primes tested up through up to 1,000,000. And so it correctly identifies all primes and composites up through 1,000,000. And I've actually the largest one that prime number that I've been able to use this technique on with my laptop is a prime around 4.2 billion, and it'll it'll actually do all the checks on this green zone within about 60 seconds, and that's basically the limit of my computer, my laptop. Yeah. So the staircase algorithm is, I devised with an algebraic expression. It only has one index because it basically will march up using a single index and then test it for the value 1. And if it is 1, then it's found a composite number, and we can exit the algorithm. If no 1 is found during this particular search, then we can say that it's a prime number. And of course, until the staircase conjecture is actually proved one way or the other, we may have to apply another test for primality, such as the temple search algorithm. So based upon this basic theory, we can explore some fundamental questions about numbers. We can tell if the square SQ of n itself, whether n is prime or composite. A more interesting question, though, is when is a natural number preceded by a prime or a composite, and when is it followed by a prime or composite? These questions basically reduce to understanding how the sequences of one square convert into those of the next square. Now, this is the spoiler alert. The number n knows that n-1 and n+1 are either prime or composite without even examining n-1 or n+1. Every number n knows the primality state of where it has come from and where it is going. Mathematically, I find this very beautiful. So how does it do this? We've seen the patterns of ones that occur for composite numbers or the lack of any pattern for prime numbers. These patterns for n-1 and n+1 actually show up in the square of n. They're shadows of these patterns of ones. And this is what my paper discusses. How do the sequences change from one number to the next when adding or subtracting 1 from n? And I've shown how primality of n can be determined for itself. If there are no 1s in the square, it's prime. If there are 1s, it'll be a composite. Now the shadows, though, of the number n-1 and n+1 will show up in the square for n. Now let's just look at this. Let's look at a set of numbers here. This is n equals 8, 9, 10, 11, and 12. And you can see the pattern of 1s for 4 of these. And then there's no 1s for the prime number n equals 11. So the question is, how do this pattern of 1s basically transform into the next pattern of 1s, which transform into this pattern of 1s, which suddenly transform into no 1s in the array, that then comes back and shows the next pattern of 1s. The paper shows how this is done. It defines rules for converting from one to the next, or from the current back to the previous set of sequences. Remember, these are all sequences, and so the paper examines a particular row and looks at how it converts to the row of the next number. there are two rules, basically. One is the forward transformation rule that goes increasing numbers, and then the reverse transformation rule that goes to uh, uh, in the reverse direction, called the reverse transformation rule, going back in the previous direction. So if we look at this, we can see a pattern or lack of pattern of the preceding square that shows up in the square for uh, 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 the square of n. So we have, for instance, um, n equals 11 here on the right with its distinctive pattern of ones. And so in n equals 11, that doesn't have any ones itself because 11 is prime. Notice the numbers in bold. That's the same pattern that is in the number that follows this. And so, the rule is fairly simple, and it's presented in the in my paper. If, for instance, there is a 2, see these 2's here, in zone 2, and I define what zones are in the paper, then these 2's will convert into 1's. And therefore, we know that if there are 2's here, the following number is going to be composite. And the same thing with 3's. If there are 3's in zone 3, then those will convert to 1's. And 4's in zone 4, those convert into 1's. So we actually have multiple ways of identifying the ones, or the shadow pattern, what I'm calling the shadow pattern, in the number for the square array for n. Now we can go in the reverse direction too. So we have n equals 9, and we see that there are 4 ones that show that n equals 9 is a composite number. And we can look and see that this pattern shows up not as ones, but as other numbers, because this one, when transformed into the sequence for the next number, will come up with these numbers in bold: 10, the 9's, and the 7. And there is a rule that says when this will occur. If we're looking solely at this array, if n shows up in the first zone, then that meant that it came from a 1 from the previous array. And therefore, we know that n equals 9 would be composite, just simply because this value of n, or 10, shows up in zone 1. And the same thing, zone 2, if 9's show up, then those also will be coming from 1 in the previous transformation. So here's the basic gist of this theory. Across the top, we have the same array: n equals 9, n equals 9, n equals 9. And then down below, we have the previous number, n equals 8, the current number, n equals 9, and the future number, the next number, n equals 10. And notice the pattern of ones. Of course, the ones for the middle two show that n equals 9 is a composite, because the ones appear actually in that array. But if we look at the first two on the left, we see that the pattern of ones, you can see them in boldface, they're going to show up not as ones, but as numbers that transform into that come from ones. And if we go to the right, we see the shadow pattern of those numbers here, based upon the rules that I define in my paper. So n knows its past, present, and future state regarding primality of itself and its immediate neighbors. And this is a novel thought in mathematics. Prior to this research, no mathematician could state that an arbitrary number of following any n would be prime or composite without running primality tests on n+1 or n-1. And this is the result described in this paper. So we took the number line, and instead of having points along the number line, we defined them as separate entities in themselves with circles and numbers of dots around the circles, labeling the numbers, and based upon that and doing the incremental counting, we came up with these arrays, these squares of sequences. And in here, each n knows whether the number before it or the number after it are prime or composite without looking at those numbers. And that's just an incredible result of this research. Now, if you remember, I did mention that each one of these rows has an orbit value, and that's the number of times it goes around the circle before it reaches the starting point again. We can take these orbit numbers and we can put them in a column, and we can take all the columns of all the orbit values for all the numbers and put them into a table. And this table is called the orbit table. And it turns out that this orbit table has its own mathematical beauty. These orbit values for each n, here's the orbit table, and the orbit values for each n, when matched with all the others in this specific triangular manner, has structure. There are many structures. There are structures on top of structures. And this is why I spent almost 2 years studying just this orbit table. I didn't even actually come up with the results that are listed in the paper because I was focused solely on understanding the structures within this. Now, my research over that 2 years is published in, it's called The Orbit Theory of Natural Numbers, and it's a 3-volume work. The first volume being fundamentals, the second volume being applications to number theory, and the third one being the collection of all the orbit, all the C++ programs I created, over 100 for the study of orbit theory. The first 2 volumes are in a large format and full color, and total close of 600 pages of research results. So I want to thank the conference organizers for providing the format for the conference, the acceptance committee for including my paper, the reviewers for their recommendations on how to improve it before publication, and all the attendees who are here at the conference, and the publication firm that will be publishing the conference proceedings. So thank you very much. I'm not sure, we might have a minute or two for questions. Feel free, here's my email address. If you have questions that aren't answered today, then feel free to email me. Let me turn it back over to you. And I can end this.